Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 40. Quick recap of what we did in the last module. We were talking about a relationship between the ultimate shear strength of the work material in terms of a component or a contribution of the normal stress in the shear plane as well as the actual shear stress component. So, in doing that we arrived at a formulation where we tried to find out the shear force, the total shear force as a function of material properties and geometric parameters. So, in fact we wrote Fs equals Wt1 tau s0 cos of phi plus lambda minus alpha divided by sine of phi times of cos of phi plus lambda minus alpha minus k1 sine of phi plus lambda minus alpha. Okay. So, from an earlier relationship which we had obtained between cutting force and shear force in the Merchant's first theory, we assumed Fc equal to Fs cos of lambda minus alpha divided by cos of phi plus lambda minus alpha. If I just substitute the value of Fs into this equation, we find out the relationship between Fc and all the material and geometric parameters, which was the way that we did it in case of Merchant's first theory. So, with the Bridgman assumptions true, we have Fc equals to Wt1 tau s0 cos of lambda minus alpha divided by sine of phi cos of phi plus lambda minus alpha minus k1 sine of phi plus lambda minus alpha. So, we now do the force velocity product. So, the average power, the minimum energy consumption for the case where the average power is represented as the force velocity product. So, Fc times of V, we are assumed to be constant. We need to minimize this. So, we definitely need to write the power equation in terms of all these different terms. Wt1 tau so cos of lambda minus alpha times of sine phi cos of phi plus lambda minus alpha minus k1 sine of phi plus lambda minus alpha times of V, and as we assumed earlier, we would assume all constancy or time invariance in case of the friction angle and a certain machining operation, the invariance of the velocity of cutting, the rake angle alpha, and constant material properties and geometrical dimensions including the width of the zone of machining as well as the uncut chip thickness. So, basically the power again W becomes only a function of phi, and minimization can be obtained by minimizing or maximizing this particular denominator here. So, I would just do the differentiation of this with respect to phi and equate that to 0. So, this becomes equal to cos of phi plus lambda minus alpha minus of k1 times of sine of phi plus lambda minus alpha plus sine of phi times the derivative of this whole term here. So, this becomes equal to minus sine of phi plus lambda minus alpha minus k1 cosine of phi plus lambda minus alpha, and so this whole term is equated to 0, and from that we are able to, if you separate these terms out, we are able to write this separately as cos of phi plus lambda minus alpha minus sine phi sine of phi plus lambda minus alpha minus of k1 times of sine phi plus lambda minus alpha times of cos phi plus cos of phi plus lambda minus alpha times of sin phi. And this is equated, hence this is equated to 0. So, the way that this can be again rewritten is cos of 2 phi plus lambda minus alpha equals k1 times of sine of 2 phi plus lambda minus alpha, meaning thereby that the 2 phi plus lambda minus alpha becomes equal to tan inverse of the value k1 or 1 by k1, I am sorry, because the sine by cos is basically the tan component, and this is actually a constant k1. So, obviously tan inverse of 1 by k1 can be treated as a constant. In other words, our condition now changes to twice phi plus lambda minus alpha equal to a constant Cm. Earlier from first theory it was pi by 2, the C1 now is something which is dependent on k1 value, which is actually the coefficient as defined by Bridgman as a multiple of which the normal stress in the shear plane would formulate a part of the ultimate yield strength and shear of the material. So, that is how the formulation here becomes a little different than the first theory of Ernst and Merchant. In fact, there are many other theories proposed by different people, and I am going to just not get into the derivation of all those anymore, but just write down some of the different results that have been obtained by various sources. So, I call this shear angle relations. The first theory of course is the one which is proposed by Ernst and Merchant. You derived this, which indicates the following optimized condition: 2 phi plus lambda minus alpha recorded as pi by 2. We have yet another Merchant's second theory, which comes into being because of the Bridgman assumptions. So, that makes 2 phi plus lambda minus alpha become equal to Cm. Then there is one theory proposed by Lee and Schaffer, where phi plus lambda minus alpha can be recorded as pi by 4. I am not going to prove this in the interest of time. And then yet another proposed by Stabler, which talks about phi plus lambda minus alpha by 2 equal to pi by 4. So, with all this on board, I think we can now proceed towards doing some numerical examples to estimate what is going to be the value of the different geometric parameters given a certain cutting condition and certain material property, and we can actually go for this optimum power consumption criteria to have a good relationship of the whole cutting process. So, I would just like to discuss this example problem here, that during an orthogonal machining operation on mild steel, the results obtained by measurement of different geometrical and force parameters are following. We have the uncut thickness T1 as 0.25 millimeters, the cut thickness or the cut chip thickness as 0.75 millimeters, the width of the cutting zone W given as 2.5 millimeters, the rake angle of 0 degrees. So, tool is actually almost perpendicular to the surface that it is cutting or scribing, and there are force measurements of the cutting as well as tangential force which are acquired mostly by the tool dynamometers kept near or just on the bottom face of the mounting or of the tool mount. So, the cutting force is recorded as 950 newtons and the tangential force is recorded as 475 newtons. We have to determine the tan of friction angle or the coefficient of friction mu, and we also want to determine the ultimate shear stress tau s of the work material. So, having said that, let us actually now try to answer the question point by point. So, we find out mu by a ratio of F by N, that is the friction force by the normal reaction, and in terms of cutting force and tangential force, F can be expressed as F c sine of alpha plus F t cos of alpha. And normal force can be expressed as F c cos of alpha minus F t sine of alpha. So, obviously, this can now, because alpha being 0, it can be recorded as F t by F c, and this becomes equal to 475 newtons by 950 newtons, which is equal to 0.5. So, that is what the friction coefficient is, mu. And the second part addressing the ultimate shear stress tau s of the work material, if the shear plane area is AS, let us say, and the shear plane angle is the angle phi, then we have phi, or we have the AS equals T1W by sine of phi, that is basically the uncut chip thickness times of width of the cutting zone, and the component T1 by sine phi along the shear plane, and the tan of phi in that case, obviously as defined earlier, is also the cutting ratio r times of cos alpha by 1 minus r sine alpha. In this case, r can be calculated to be a third, so T1 by T2 basically, which is 0.25 by 0.75 as defined in the problem, 1/3. So, tan phi becomes equal to 1/3 cos of 0 degrees divided by 1 minus 1 by 3 sine of 0 degrees. So, it is basically 1/3. So, phi becomes equal to the tan inverse of 0.333 1/3, which is 18.4 degrees. So, that is how you calculate the phi. Also, the AS, or the shear plane area, in this particular case is basically equal to the uncut chip thickness T1 times of the width of the machining zone, also recorded as 2.5 mm in the problem, divided by sine of phi, or sine of 18.4 degrees mm square, which basically comes out to be 1.98 mm square. And if I wanted to look at what is the value of Fs, so Fs can again be recorded as a combination of the cutting force Fc and also the tangential force Ft as recorded in the cutting zone as Fc cos phi minus Ft sin phi. Look at the equations that have been illustrated earlier. So, in this case, this would be 950 times of cos of 18.4 degrees, which comes out to be about 0.95, minus of 475 times of sine of 18.4 degrees, which actually comes out to be 0.316. So, the totality comes out to be 751.3 newtons. So, obviously, the tau s, or the shear stress in this case, is shear force per unit the shear plane area. So, 751.3 divided by the shear plane area, which is 1.98 Newton per millimeter square, which comes out to be 379.4 Newton per millimeter square. So, that is how you actually tackle these problems about the different unknowns, like what would be the shear strength, ultimate shear strength in the zone of cut, etc., by looking at the geometrical parameters and also looking at the measured forces of in the cutting and the tangential direction at the zone of cut. So, with this I would like to end this topic. There are many more topics to cover, including what is going to be the temperature distribution of the cutting zone, as well as what is going to be the specific energy of cut which is needed, but we will do this in the subsequent module. Thank you as of now.